All good?
Yeah.
Okay. Hi, everyone. Oh, I forgot this. Okay. Hi, everyone. Okay, I'm just gonna shove this into my pocket and then I'll start. Okay, that's good. That's good, right? Yeah. Okay, cool. Okay, nice. Hi, everyone. So today I'll be talking about permutation action on Chow rings of matroids. I'll define all of these things in the talk. Oh yeah, I should say I'm from University of Minnesota, and I'll be talking about joint work with Robbie Angaroni, who's there, and my advisor, Vic Reiner. Um, so what in like overview, big picture, this will be Chow rings of matroids are like a recently popular object, and we used representation theory tools to study it and strengthen known results and like form more informed conjectures on things that were not, conjectures, so they're not known before that. Is there a way for me to like switch slides without walking up to this? It's okay if not. That's okay. I can walk. Um, and I also don't need to be away that much. Okay. Okay. Yes. So no, I should be fine. Okay. So for background, I'll talk about what matroids are. I'll talk about the motivation of this problem. Then I'll talk about what Chow rings are and what permutation action, group action, what I mean by that. Then I'll talk about our work, which I describe as creating equivariant maps between G sets. Then I'll talk about future work, which is building some evidence towards other equivariant conjectures and other rings we can think about, we can apply this thinking to. So when I'm talking about a matroid, I'm thinking of a combinatorial structure that is defined on a ground set E, which is just some finite set, and it's defined by its lattice of flats. So a flat is a subset of the ground set that has some sort of closure. If I am thinking of the ground set, in the case that my ground set is a set of vectors, then flats are subsets of that ground set that are maximal with respect to the dimension of the span. So, for example, if I have my ground set is E1, E2, E3, and the vector E2 plus E3, the set E1 and E3, E1 and E3, that, right, their span only contains E1 and E3. But the set E2, E3 is not a flat because it also contains, right, their span also contains E2 plus E3. So it is not maximal with respect to that. So this is not a flat, but the set E2, E3, and E2 plus E3 is a flat. I should say also, I meant to say this at the start. So I'm, maybe so I'm a graduate student, right? I don't have as extensive knowledge. I think, I guess maybe I would classify myself as more of a combinatorialist, or someone that does combinatorial commutative algebra or algebraic combinatorics. So I might be coming at this from a different perspective than you are. If you have any questions throughout this, please ask me. I'm like, I might be accidentally sweeping some combinatorial detail under the rug. I might be sweeping some algebraic detail under the rug. And don't let me do that. Please ask me questions. I'm so happy to clarify whatever I'm saying. Okay, so matroids that come from where the ground set is a set of vectors, that's like one type of matroid called a representable matroid. It's like where, in this case also, a matroid is a matrix, so that's where, or like it's defined by the matrix, so that's where the like word matroid comes from. But we can expand our definition of matroids to things that are not representable. So one such or different class of matroids comes from where the ground set is the hedge set of a graph. And when that is the case, a flat is a transitively closed subgraph. What I mean by that is something like this, where I'm taking the edges 1 and 2 in this complete graph on 4 vertices. So if I'm taking the edges 1 and 2, this is not a transitively closed set because I contain this vertex and this vertex, but I'm not including the edge between them. But if I include the edge 5, then I do have a flat. If I organize my flats in, into a closed set, with inclusion being the relation, I get a really nice post set. I get a lattice that we call a lattice of flats that I'll note with this math cal L. So this is the lattice of flats for this situation. This is the lattice of flats for this situation. All flats have a rank, which is this sort of maximal closure, right? Whatever that is. I have a lattice of flats, so I can just think of, right, and this is a rank post set, so I can think of the rank as being the rank of the element in the post set. So like this is rank 0, this is rank 1, 2, and 3. And I'll also refer to the rank of a matroid. That is the rank of the ground set, which I'll say is R plus 1 for our convenience. Okay, and the rank of the ground set in the lattice. We can think of it as that. Okay, questions? Okay, so matroids are like, became popular within the past decade because of something called the characteristic polynomial. So a characteristic polynomial is something that can be defined on any post set. We will be, of course, thinking about it on the lattice of flats, but in general, characteristic polynomial is defined. So I have an x raised to the complement of its rank in that post set. And the coefficient of it is defined by the Mobius function, where Mobius function is a function that's defined recursively. Let's see it on this example. I think maybe the definition is not the most friendly looking, but the example I feel like makes it clear. Okay, so the bottommost element, the empty set, gets a 1 with the Mobius function. Everything in this next row gets a value of -1 because they, right, the only thing under them is something with a value of 1, and I'm doing the negative sum of that. Then element 2, 4 will get a value of 1, and the elements 1, 4, 6 will get the value of 2 because there are 3 things under it here. So it gets -3 plus 1. I want them to add up to 0. And the top, okay. This is like, maybe if I want to get a characteristic polynomial, this is kind of annoying to do every single one. So we can organize these Mobius values into something called the Whitney numbers of the first kind, where WK, a Whitney number, is the sum of all of the Mobius value function, all of the Mobius values for a particular rank K. So for this post set, and that lets me write this more cleanly. So for this post set, my Whitney numbers are 1, -6, 11, and -6. And my characteristic polynomial is this for this post set. So the sequence of Whitney numbers of the first kind was conjectured to be log concave for any matroid since the 60s. So this was first conjectured in 68. And for something to be log concave, that means that the ith element in that sequence squared is greater or equal to than the ones around it, right? The preceding and proceeding element in that sequence. Sorry. Okay. And let's just do a sanity check, right? W2 squared. Okay, 11 squared is definitely bigger than 6, and 6 squared is definitely bigger than 11. So, okay, conjecture not disproven yet. So, in fact, okay, this is called affirming conjecture, so must have been true somehow. And this and many other related conjectures were affirmed by Adibur Sitaha and Katz in 2015. So this was open for quite some time. And they did this by proving that the Chow ring of a matroid satisfies something called the Kähler package. So what is this Chow ring? The Chow ring of a matroid is a polynomial ring where I have a variable for every non-empty flat of the matroid. So the ring for this guy will have 6, 7, 1. So we'll have 14 variables, and I'll say what the ideals are on the next slide. But both of these ideals are homogeneous. So I have a nice ranked, or yeah, I have a graded ring. So I can then talk about the graded pieces of this ring. And the highest graded piece is of degree 1 less than the rank of the matroid. The Kähler package, it has many, it says a bit more than this, but for our purposes, the Kähler package, the consequence of it is that complementary degrees in the sequence of vector spaces of the Chow ring are symmetric, meaning that complementary degrees are isomorphic, and unimodal, meaning that up to the halfway point, I can inject the smaller vector space into the larger one. I mentioned lock concavity, but lock concavity of this is only conjectured. It's been proven in very recently in some particular cases. Okay, so more on the Chow ring, which is my object of interest. So let's say I have a rank +1 matroid. We already said it's a graded ring. The ideals for this ring are the Stanley-Reisner ideal, where I quotient by things that are incomparable. So like x2, x1, 4, 6, or x2, x3 live in this ideal. And I also have an ideal that consists of linear forms where I take an atom, so a rank 1 element, and I sum up all of the flats that all of the variables that are supported on flats that contain it. So for example, I can have like x1 plus x125 plus x13, x146 plus xe. That would be one of the linear forms in here. So this ring was defined by Feitner and Uzvinsky in 2003. And also very kindly, they provided us with a basis for the Chow ring, meaning that that the ring is a Z module over this basis, where the basis is a product of variables that are supported on a chain, where the degree of each variable is bounded above by the difference of the rank of the flat that it belongs to, and the preceding flat minus 1. We'll call these Feitner-Uzvinsky monomials, and we can also break them up into subsets based on their degree, and each the degree k monomials form a basis for the kth graded piece of the Chow ring. Yes. Oh, that is a good question. I think so, but I'm like, can you tell me what Artinian means, and then I will. Yes, yes, and it's not obvious that it is, but if we take a look at this basis, and we'll do that in the next slide. So yes, thanks to having this basis. It's not like totally obvious before that. There's no reason why it should stop. Yeah. Good. Any other questions? Okay, let's do an example. So let's take, I wanted to have a big example, but to do this with. So let's do it using the Boolean matroid on 5. So all subsets of 1 through 5, where I omitted the lines because that would be very messy. So let's go through and see what what the bases for the Chow ring of this guy are. So, okay, degree 1 basis, I only know of one. Cool. Let's see, degree 1 basis, I should just get the variables of my ring, but I don't get variables that are supported on the one element subsets because of this degree bound. So I have to be right in a single variable monomial. I have to be one less than the rank. And so I cannot have, according to this rule, I cannot have elements that rank xi in this, right? Because they are of rank 1. Is that okay? Does that make sense? Okay. So then degree 2, for the same reason, I cannot square xij, but I can now get some mixed monomials, right? I can get xij times xe, I can get xijk times xe, and I get this guy in pink. But this degree condition forbids things of consecutive rank, right? Forbids me from having like xij, xijk. Now degree 3 monomials, I can get these guys where I can increase the degree on xe for these blue guys, increase the degree on xijk here, but I can't raise the degree on xe because then that would go above this, right? That would violate this, but I can cube these guys. And degree 4 monomial, I just have one as well. So maybe I want to get the Hilbert series of this. I can do that right by counting up the number of each basis that I have, and I get this nice sequence. It's certainly symmetric and unimodal. In fact, this one is Eulerian, but that's only the case for the Boolean matroids. But the symmetric and unimodality property, right, that better apply to all of them since someone proved that it does. Okay, so as we said, okay, these dimensions form symmetric and unimodal sequences. This is also proven to be true for them as vector spaces. Also, it's as a consequence of the Kähler package, and this is all like consequences of the Kähler package. This is also true for these as G representations. But what we show is that this is true of the basis if we view them as, if we have equivariant maps that map between G sets. So the difference between these two is that we are mapping bases to bases rather than mapping bases to some linear combinations of bases. But I'm saying these are G sets, G representations. Let's take a look at what that means. Just to be sure. So when I'm talking about group action, I want to think about, in this case, I'm thinking of group action of the action of the automorphism group of the matroid. And so automorphism group, I want to preserve the structure of the matroid, but that means I want to preserve the poset here. The automorphism group for this poset is the permutation group generated by swapping. I feel like it's easier to see with a graph. If I swap 1 and 3, then I can also swap 3 and 6. I can also swap 1 and 6, and then swap 3 and 5, or I could swap 1, 2, and 3, 4, and still get the same, right? I'm just relabeling things. This is turns out to just be a symmetric group on 4 elements. I can think of that as like the symmetric group on these 4 vertices. Okay, so how do we think of this? So I want to consider some subgroup of the automorphism group as my group that I'll be acting by. So I claim that the Chow ring is a representation of this subgroup G. I can extend the action of G onto the ring by sending each variable to the image of, right, to where my group G would send the flat, right? So I'm doing something with flats when I'm acting by this group, so then I just extend that action to the variables. Yes. Yes. Yeah, so ours is integral. This, I believe, is over the complex numbers. Yeah. Cool. Okay. Good. Oh, I don't know where I went. Sorry, that went way. Okay. I also claim, okay, so we extend the action, and I claim that this action preserves the ideals because I'm not going to, right after my action, I cannot change two things that were incomparable before are going to stay incomparable. And two things that, right, if one element was contained in something else, then it will still do that after I act. So my ideals are preserved, which means that the ring is a representation of that group because it's stable under that action. Okay, but even further, the ring is a permutation representation, meaning that any automorphism group, just like it didn't, right, I just said it doesn't change inclusion, and it doesn't change, because it doesn't change inclusion, it's not going to change the degree of monomial, so it actually just sends bases to bases, which makes it a permutation action. So it just permutes the bases. Let's see that in our example. So if I act on like 1, 2, 3, 4, 5 onto an element of my basis that we saw in the previous example, I just get something that like is of the same form, just relabeled, right? And it's still, right, I sent a degree 2 element to a degree 2 element and a basis to a basis. And in general, any monomial, right, this would be true for any monomial, I will send things that are in degree k to things that are in degree k, because these, right, that means these degrees added up to k, and that is not going to change because I'm preserving containment. Okay. So now I want to talk about our work. So again, my goal is to get these maps and get them in some equivariant way. I guess before that, I should pause for questions just to make sure. I'm to drink some water. Okay. What am I? Oh, I see what's going on. Okay. This is a misclicking on this. Okay, cool. I'm going to stop doing that. Okay, so I want to send things that have the same stabilizer under the action of G. So I can think of that as, right, I want to like create a set that has that property. So we call that the extended support of a monomial, where I take the support of that monomial and I can add the ground set to it because any action on that will be trivial, right? It's obviously going to be stable. Then I'm going to define the order on these monomials by saying that something is below, right? Monomial A is below monomial B if A divides B and they have the equivalent support. And this order generates a nice distributive lattice like this. So in this example, we have some random matroid, right? I need a kind of a big example for this to be nice. So let's say I've got a rank 10 matroid, and I have a pair of nested flats where F is of rank 3 and F prime is of rank 7. So, and then these are all of the monomials that have the extended support of F, F prime, and E, or F, F prime, and E, yes. And these are all of the monomials I can get with that. So these are all bases in my of my Chow ring, and all of these are things that I want to like send to one, right? Like if I'm going to send this somewhere, it's got to be one of these three to preserve its stabilizer ring. One thing we may notice is that I can think of these as like how much can I raise, to what degree can I raise the variable xf in this monomial? Because of its rank, it can only go up to degree 2. F prime, because of its difference with the rank of F, I can raise its power up to 3. And E, I can raise its power up to, from 0 to 2. And I can think of this distributive lattice as the product of, just the product of intervals, right? I could go from 1 to 2, 1 to 3, 3 to 2. And that is helpful because every product of intervals has something called a symmetric chain decomposition, which means I can take my distributive lattice and separate things into it, separate all of the elements in my lattice into symmetric chains. So they're symmetric around the middle, right? If I contain the bottommost element, I have to contain the topmost element. And so every monomial lies on a unique chain because I've partitioned my subset. So then what we do is map our monomials along this chain. So if I want to map it to a, right, if I want to create a map from a degree k monomial to degree r minus k monomial, I just go to the complementary position along the chain. And if I want to map it to the next one, I just map it along the chain as well. I have that here. Okay, so and this map creates a bijection between complementary bases, and this map creates an injection. So I could send, you know, if this is my symmetric chain decompositions, I have a few options with, and we just say pick one. And so I send this guy to this guy, this to this, if I want a unimodal function. And, you know, then this necessarily, if I want to create this function pi, then this guy goes to this, right? Okay, so I have these maps, but having fixed the support, the action of G will commute with either one of my maps. So that means that I have created a G equivariant bijection of these that gives me symmetric, right? That gives me things that give me a symmetric sequence, meaning that, right, I have a G equivariant bijection between complementary degree pieces or complementary bases, and I have an injection from kth piece to k+1 piece. Okay, so then future directions that I want to talk about. Oh, well, I'll talk about other directions this can take, but maybe I should also pause for water and questions. Yes, yeah. Yeah, yeah. Yeah, so totally, yeah. So the symmetric chain decomposition does all of the work for us. It's true. How do we know that this always exists? That is like, this is a, I just click, yeah. So it is a like known fact that a product of intervals like this always has a symmetric chain decomposition. So like maybe putting this out felt a little silly at the time, like sure, yeah, I can raise f to, from 1 to 2 and so on. But because I have this and I have a clear definition of how to get this, it's just the difference of degrees, right? So it's what I can raise f to, what I can raise f prime to, or possible degrees for xf, possible degrees for xf prime, and this is possible degrees for e. Then, right, I have a clear, easy definition of these. Therefore, I have a clear pathway to a symmetric chain decomposition. Yes. Yes, yes. Yeah, totally. Okay. So so I should say, just taking a step back, maybe looking at what we did, we can think of things, right, in the virtual character ring, where if I say things are equivariantly non-negative, that means that that thing that's equivariantly non-negative is a positive linear combination of irreducible representations of that group. That was close. Good. Okay, wait, oops. Okay, perfect. This is, that means, so like the Chow ring of, so the Chow ring of that graph that I had earlier, this guy, that breaks up into three graded pieces. And I can think of that as, right, A0 is the trivial, can be written as trivial representation. Then I have 3 copies of trivial in my degree 1 basis, and this guy and this guy. But showing that something is a permutation representation, I can think of that as showing that something is Burnside non-negative. And so what we did in the previous slides is show, for example, Burnside non-negativity of the monomials of degree k plus 1 minus monomials of degree k. This is just, I think I'm gonna just try to get some water out of this. But I think it's all good. Okay, cool. Okay, so unimodality that we talked about lies at the bottom of a hierarchy of statements of sequences, where real rootedness is the strongest statement, but along the way, there's also log concavity, which we talked about, and gamma positivity, which we don't need to know the definition of for this. So these are all conjectures that have not been proven for the graded pieces of the Chow ring. I should say that non-equivariant gamma non-negativity was proven last year by Ferroni, Mather, and Stevenson-Becky, and also separately by Wang, and also separately by Xin-Che Liao. And non-equivariant real rootedness and log concavity are still only conjectured. So things that we conjecture include Burnside log concavity, which means that the degree J monomials and degree K multiplied by the degree K monomials are Burnside bigger, or Burnside, the difference of this minus this is Burnside non-negative. This is thought of as when the degrees add up to the same thing. That's called strong log concavity. And before we saw I'll just write this on the side here. Earlier I wrote wi squared is greater or equal to wi minus 1 times wi plus 1. This is called weak law concavity, and so stronger would be wi w. Did I use j? W. I use j and k. Okay, j k is greater or equal to I and L, where I plus L is equivalent to j plus k. So this is a slight generalization of this statement. Okay. So a piece that contributes to this conjecture is that we've shown that we can always insert the degree j plus k pieces into the degree j times degree k pieces, because we can always just factor. And this proves log concavity, Burnside log concavity, for all matroids up to rank 6, which is a large number. After rank 6, at rank 7, we get things that we can't just factor as easily. So it's not it's not that it breaks down, it's just that it doesn't follow this neat pattern. No. So equivariant log concavity is not known. Yeah. Good question. Yeah, no. I mean, yeah, no. No, I don't think so. I mean, I think there were some like conjectures towards it, but yeah, not like, or like experimental evidence. Like I know Ferroni and Stevens, what's his name? Yeah, they have a, they like have some supercomputer that they run, I've heard them say like, oh yeah, we have a thing that disproves it of a rank 83 matroid disproves that. So they were, so like they probably had like evidence from the supercomputer, but not like a proof, right? Then I also want to mention equivariant real rootedness. So in general, real rootedness is that this polynomial is real rooted if and only if a minor of this matrix is non-negative. But real rooted means that like this polynomial has real roots, but you can recharacterize that in terms of having non-negative minors of this matrix. And so equivariant real rootedness, right? And okay, here's a minor particular example. Equivariant real rootedness means that instead of having the degrees, we will have the actual vector spaces, and then we have an equivariant map that shows that this is greater than 0. Right? And so to prove, we have evidence towards equivariant real rootedness by showing that, minors that look like this with A1s on the diagonal are equivariantly non-negative using causality. So see how that works. So in 2022, McCullough and Mastroni showed that Chow rings are causal. And so, right, what does causal mean? I feel like this is an audience that does not want a definition of causality. Maybe you're all good. I'm not sure. Okay, so right, that means I have a complex tensor products where each one of these is a tensor product of my graded pieces, where I then like coarsen, right? I have some set of them, and then I coarsen them as I go through. Let's see. Example. Oh, and this complex is stable under the action of the automorphism group. And so maybe I take 2, 1, 1. I get the exact sequence that looks like this for my causality. And as a consequence of the causality, right, that this is an exact complex or exact sequence, I get that these determinants are non-negative. So, right, I'm like solving for this kernel, for the character of this kernel, because I care about equivariance. I have to care about the character values. So I get an alternating sum of the preceding pieces. And I get this. So in particular, I get, for this example, I get this character identity. So I get that, like, this determinant specifically is non-negative because of the causality. But I can extend that to, okay, yeah. Well, that's fine. Okay, so I can then extend this to show that all of these give genuine representations. So where I have A once on the diagonal. And okay, so I've switched from talking about the graded pieces of the Chow ring to, or right now I'm talking about the graded pieces of the Chow ring, but before I was talking about the monomial basis of it. Maybe that's disturbing, but it's harder to think about these with the monomial basis. But we have, so we conjecture that these determinants are not just equivariantly positive. We hope, we conjecture that they are Burnside non-negative. And in particular, we have shown that these minor specifically of the bases are Burnside non-negative, which means I can inject these bases into these bases. So like degree 2 bases multiplied by degree 1 bases, right? And degree 1 multiplied by degree 2. So, you know. Okay, yeah. And so I can inject these guys into this, right? Because this would be my negative piece. And this is my positive piece. Okay. I've got, how much time? I think like, okay, yeah, cool. Okay, so that's my, okay, that's what I wanted to say about other, like, yeah, things that are stronger than unimodality. But another thing I've been thinking about are other fans and other Chow rings. So I'll say a bit more about that. So in general, maybe if you have heard of Chow rings before this, maybe you've heard of them as like the cohomology rings of a variety. And so specifically, the Chow ring of a matroid, I've just been saying, oh, it's the Chow ring of a matroid. But it's really the Chow ring of the Bergman fan that is defined by the matroid. This fan has rays that are defined by the flats of the matroid that are non-empty and not the whole set. And the whole set would just like add another degree that we don't need. And its cones correspond to chains in the lattice of flats. So for the smaller example we saw at the very beginning, this is the fan for it. Where it's like, I should say, right? My biggest chains, if I eliminate these guys, my longest chains are, something from here to here, right? I only have 2-element chains. And so I get 2-element, or I get cones of degree 2 because of that. And my rays, so like I have 8 flats that are not empty and not and proper, meaning that they're not the whole ground set. And so I have 8 rays here. So one natural question is, what other fans can we consider the Chow ring of? And can we use group action to understand those as well? Right, this is like, the Bergman fan is like, has a more complicated and, a more complicated cousin called the conormal fan, and like much younger cousin. Bergman fan was defined in like 2003. Conormal fan was defined in like 2020. And it uses data of the matroid and its dual matroid. And yeah, it's defined by this, instead of being defined by flats, it's defined by data that's analogous to flats, but also incorporates data of the dual matroid. So we'll look at example of that. I think that'll be it. Oh, that's so ugly. I'm sorry. Uh, some text is supposed to fade away. Okay. Oh, sorry to make you look at this atrocity. I'll I'll write it on the side. Okay, so we have an analog to a flat called a biflat. Oh, okay. So a biflat um, means is written as F bar G, where F is a flat of the matroid and G is a flat of the dual matroid, which I'll explain what that is here. And a biflat must have that F union G is the ground set, but they're not both the ground set. So let's take this little matroid defined by this graph. Its flats are 1, 2, right? This is my closed set of edges, then 3 and 4. And then once I take any two of them, I get the closure of the whole graph. And the dual matroid, if my matroid is a graph, is the matroid that corresponds to the dual graph. But if it's not a graphical matroid, then the dual is like more annoying to find. So this is the dual matroid to this guy. And the biflats of this matroid are, I can take E and the empty set and right in both directions. And then I can take like any flat and attach E to it, or I can take any flat of the dual matroid, attach E to it. But I can also take 1, 2, and 3, 4. Those are my biflats, and these define the conormal Chow ring of a matroid, where I still have a variable for each biflat. And the Stanley-Reisner ideal becomes a little bit more complicated in that before I could have said, oh, these need to form a flag. Here, they need to, to not live here, they need to form a biflag, but a biflag is a little bit more complicated than a flag, and I'll have that in the next slide, but we'll see, maybe we won't need it. And the linear forms are pretty much the same as they were before. This ring also happens to be graded. And yeah, okay. And then this thing that's covering the pieces that I need is, right, I would love to do what I did for the normal Chow ring and do some algebra on it and figure out nice things about the Chow ring and show that it's got these symmetric unimodal properties. That'd be awesome. But to do that, I need to find a nice Grosvenor basis, right? We were able to do all of this stuff because we have this Grosvenor basis that is closed under the action of the automorphism group. And that Grosvenor basis allowed us to have these nice standard monomials, right? I was working with the monomials, and I could only get to them because of this Grosvenor basis. So something I've been working on is finding a nice Grosvenor basis for this ring and finding a nice Grosvenor basis for another Chow ring of another fan that I will not mention here. But so this problem, right, these objects that people care about in algebraic geometry and in combinatorics, what it all comes down to is like having a Grosvenor basis that's nice. And so it just comes down to algebra. So I felt that this was appropriate. Okay. I think with that, okay. Yeah. And then I talk about biflags. I think we'll, we have this, what I don't just want them to contain each other. I want for there to be a gap index. I think I'll stop here because I see it's about time. So I will stop here. Oh, thank you.
any questions for Anastasia?
The co-normal challenge, you said it's graded, was it just Z graded?
Yeah, it's just Z graded. Yeah, yeah. And it's top degree is 2 less than the ground set. Yeah.
And do you know if these co-normal challenge also have our kazoo or not?
I don't know that. No. Yeah, no. I think there is evidence towards them being so because they are homotopically equivalent to the product of the Bergman fans, or the complex is whatever. So they're like pretty close to a Bergman fan with a little bit of more complexity. So their Hilbert series is like kind of the product of the two normal Matroid Hilbert series. So that is like nice in that way. I could say more. I'm just like skipping over some annoying
I'm
definitions.
just wondering.
Yeah, yes.
Back like
Yeah.
Jason and Matt Mastroni.
Yeah.
That these are, so somehow.
Yeah, I think that would be nice because they don't use the they're not using the Grosvenor basis to prove their result, right? That would be really nice, but they had to do things that are more complicated. So yeah, I think it's possible, but I've not worked too much with it. But I think it would be nice to know that because these rings are like really unruly. And when I talk to like the co-normal Chow rings and when I've talked to the people that defined this and I've said, oh, I'm working on this, they go, oh my God, that's so nice. Those things are so annoying. I'm glad someone's doing something with them. Just want them to be, I mean, like the calculations get really out of hand. Like I had to do this little example because any bigger example is like overwhelms the computer. Yeah. Yeah. But yeah, I think it's possible to do that. Yeah. 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 So Lefschetzness gives us where are we? Okay. Lefschetzness gives us this like unimodal unimodality of G representations is given to us by multiplying by the Lefschetz element, which in this case is just xe. But that is not like multiplying by the same element is not going to preserve bases. And so there is no, I can't talk about Burnside Lefschetzness because it's just like that construction doesn't work. It's a good question. I'm not sure. But I mean, like I could tell you what it is for this Chow ring. So it's the way that Adipersitoha and Katz define the Chow ring that, so here they also eliminate xe as one of the variables for like algebraic geometry reasons. And then this, instead of this sum, it becomes the difference of sums of things that contain an atom. And so then the Lefschetz element is something we would call xe. And we add in xe because it makes things representation theory nice. And like xe is like important to our story. But so this guy, yeah, the Lefschetz element is it's like the sum of, it's literally this guy, actually. It's just all flats that contain an atom, and it doesn't matter which atom you use. So like x1 plus x125, x13, x145 is a Lefschetz element. But yeah, does that answer your question? I'm not totally sure if it's, I guess I don't know the I guess. Yes. Okay, thank you. Yes, I think what I realized is that I'm not sure about the difference between strong and weak left shifts. But yes, now that you've said it, yes, powers of it also work. Totally. Thanks. Yeah.
Things like almost,
Yeah, yeah. And yeah, I mean, for this one, I can think of it as the symmetric group on these vertices. So in general, I guess, I guess your question is, do I always have a nice way of thinking about the automorphism group on any matroid? I yes. Oh, yeah, I think it's always going to be S K, where K is the number of vertices. Yes. Oh, I I think so. Yeah, I mean, this like, yeah, like having this be like a nice product of these guys, I think, yeah. Oh, yes, yeah, that's always the case um, because of the unimodality. So I have to insert that. Yeah, yeah. Yes. And like that's going to be true for any matroid because I have unimodality of representations. Yeah. Yeah.
I don't know if this question makes sense, but do you know if your work has K-theory connection?
So that's a good question. Right, K-theory is what gives us this that the Chow ring is the cohomology ring. And yeah, I mean, I can say that if I'm thinking of cohomology, I guess in the context that I'm thinking of the cohomology ring in this, what I'm most often thinking about it is the Chow ring of the matroid with a different building set. So in particular, if I take the Chow ring with the minimal building set, which like means that I eliminate these two element guys from this, from my set of flats, and that adds like a different relation, then the Chow ring of that is the cohomology ring of the, oh my God, I'm like forgetting the word. Oh my God. M0 n bar, M0 n plus one. So like in this case, it would be M0 5 bar. Oh my God, why am I forgetting that word? What's up? Yeah, moduli space. Sorry, yeah, that is. I'm forgetting the word moduli. Okay, so yeah, this then connects to the cohomology of the moduli space of genus zero curves and n plus one points. And so for that, we can show that this works if we add an extra condition on the group action. So we thought that it worked for a bit, and then we realized that it didn't because of an extra condition that we need to add in. So this does have K-theory implications, yeah, but it is like sometimes I have to make it more complicated. Yeah.
So this is fairly abstract, but like in speaking of classical algebraic geometry, OpenC.
Yeah, sure.
Complex projective varieties.
Yeah.
Like this gives a lot of nice examples. Like so, if you were gonna like study the Hodge conjecture or something.
Yeah, this does give nice examples, but I think this like from what I understand, and I would not classify myself as a algebraic geometry expert, but from what I understand, this like breakdown on the monomial basis doesn't do that much for algebraic geometry. Like, so it like has some K-theory implications, but it's not that I have not seen how this can be applied to solve something in algebraic geometry, but there are many things I don't know. So maybe it is, and I'm underselling myself. Yeah. But I'd love to talk about it, I think. Yeah, just because I'm not like,
I'm more
Yeah.
practical minded than like seems like a lot of these talks are generalization for its own sake, but
yeah, I mean, this gives us, right, like this gives me a whole new toolbox to work with, right? So I'm like generalizing um, symmetry, or I'm like categorifying it because I get new tools, meaning representation theory tools. But, right, those tools might not, it would be really awesome if they meant things in algebraic geometry, but it's not, I have not seen that, but like, again, I've been wrong many times. Yeah, yeah. How does that?
Take one more
Yeah.
question.
Oh, it's okay, close, yeah. Yes. Yeah. Yes. Yes. So the conormal fan is like can be thought of as a Lagrangian. I mean, it's like defined as a Lagrangian fan, and Lagrange from like Lagrangian is used in that context because they use data of the matroid and the dual, and so it's I think Lagrangian just means that in their context. So I did not come up with the word Lagrangian for this. This is what Ardila, Denham, and Ha used to define the conormal fan. And I think like the two papers that talk about it are called Lagrangian geometry of matroids and Lagrangian combinatorics of matroids. And then that's the title. And then they just talk about this conormal fan. And so then like the Lagrangian, because then instead of the Bergman fan, the Lagrangian analog of it is the conormal fan because it is defined by now not just the data of the matroid, but also by the dual matroid. Then the Lagrangian analog of flats is the thing that defines the conormal fan, which are biflats. So that's that's why that word is used. Yeah. Yeah. You. Nice algebraic geometry object, and it deals with what do they do with it? Yeah, I don't think it's like that it's the reverse of normal. I think there's some, right, like it's, I think of co as like, I guess in the category theory sense. I don't think it's that, but it's, there's some reason for that word, but I don't think it's in the category theory sense, but it might be in the geometry sense. Yeah. Yeah. Sorry, I couldn't answer that more. Yeah.
Let's thank Anastasia again. And so just a reminder, so Turbo Talks will start at 12. There is still time to sign up. So yeah, so it will just be a short, like 5-minute talk or less about some open problem if you're interested.
Or if you want to learn about anything.
I do have like an open question. However, I will actually include it in the
Hey. Yeah, totally. I think I didn't totally understand it.
Okay, so
honestly.
in this like example that you kept just
Yeah.
going back to,
Yeah.
like each created piece you like broke down in this example, like live representations showed up.
Yes.
It
Yeah.
did like a complete graph
Yes.
all the number of vertices, like
Yes.
how easy would be to write down or like what representation is feel.
It would be, okay, I mean, it's much easier for this one, but I think it's not hard for the other ones. I think I could do
I
it.
feel like
Yeah.
know what was, maybe not the multiples.
Yeah, because it depends. I guess the way I think of it is.
Yeah. I mean, yeah, register me.
Okay, sure.
Yeah, register me. And most likely, right now, what I'm thinking is that I will say, okay, there is this open question, more context later in the
Yeah.
talk.
Yeah, that seems good.
That's okay. Where is the link?
I think it's outside by the coffee shop. The list is by the coffee, right?
Say that again?
The list for Turbo Talk?
Yes.
By the coffee?
Sure.
Yeah, thank you.
Thank you.
We should take it.
I mean, this is insane. Yeah.
Yeah. Oh, man, I agree. I was sure. Wait, let's show you this. You need one real resolution to that. Then it's like, yeah. But it's
Northwest?
Right.
Oh, I thought it was, what about the like the orbit?
We'll coordinate it. Okay, yeah. I was gonna look into the photo. I was thinking, I don't really want to do a photo talk about it because like I know. Like, I need to go. Yeah.
Sure, they're, if I do like the first.
Well, nobody has officially signed up, and I think you'll be on the side.
Sorry.
Yeah.
Yeah. That'll do it, like.
Yeah, I just want to make sure that it's always.
Totally, yeah.
It's a topic that somebody gave to talk to the other.
And that's always the case, too. It's always the private.
So it's like. But you don't, it's not, you need to.